Hello. In this video, I will make an overview on the congestion control contest that is the next programming assignment of our course. So I'll start by talking a bit about design contests. This type of assignments are very common in various computer science fields like data mining and natural language processing, but usually not common in networking or systems teaching. So, and this is largely due to research in network systems to be complicated, and it's usually carried out largely by professional researchers at these, large industrial labs like Microsoft or Google, etc., or companies, or at academic institutions that have good test beds and large-scale test beds to make them. And this basically limits the number of people that are able, to design new research protocols, etc. So the question is, how can we open up networking research problems to a wider audience? And this is where protocol design contests enter. They are very rare yet, but the goal of the few that exist are basically three. One is promoting reproducible research. This is very important from a scientific perspective, the fact that we have systems and networks that we can, and experiments that we can reproduce, and this is something that is required in a protocol design contest. Also helps publicizing research to a wider audience, as I said before. And as you will see also during this video, may even provide lasting advances to the state of the art of networking research. The problem is, as I said, network systems are complex. They often involve engineering trade-offs. It's expensive to build large real-scale test beds to test our protocols or our network solutions, and so this is usually difficult. However, there are a few exceptions to the rule, or maybe not just a few, even several exceptions, and one is congestion control. Congestion control is one of those fields and one of the very, very important fields in computer networks where it is possible to do this sort of things. And we will do this in this course with a congestion control contest. So the idea of the next programming assignment is for students to compete to build the best congestion control algorithm they can to maximize a certain metric, which I call here power, which is basically throughput over delay, which is the goal is to have maximized throughput and minimized delay on a specific emulated cellular network. So the target is a cellular network, which is different from other types of networks. So it has its own very specific characteristics, as we've talked in one of the recent lectures. And also we are considering like more interactive type of applications like video, conversations in video or audio, especially video that requires high throughput. These applications require high throughput, low delay, so they are very intensive for the network. So I will start by acknowledging Keith Winstein, who was basically the mentor of the first congestion control contest, and this one that basically we will use. We will use Keith's code basically with slight changes, and also Nick McEwen, who is the main person of the Stanford course that we're following. If you want more detail, you can check this paper also by Keith and his co-authors on CCR July 2014. So with respect with the infrastructure, so we have CellSim, which is a cellular simulator. We have this on top. So we're running this. We can run this like on a bare metal machine, like on your laptop, or where probably you'll have better results than running in a virtual machine. But you can also run it in a virtual machine. We basically provided you with one already set up. You could also run this on an EC2 instance. In fact, there are free instances that you can try to use if you want. And so we are given a trace, a cellular packet delivery trace on top, which basically it's real data from a cellular network that feeds a cellular simulator, which is a network emulator, in fact. And there is a sender and a receiver that these were already coded, so you already have the code for this. And then this generates an output trace that is sent to a contest server, and the server replies with an URL that has delay graphs and will tell you what's your score in the contest. So this is the infrastructure that we have. With respect to the design of the contest, so you have most code is already available. So you already have a protocol implementation skeleton that is customizable, and basically the idea is that you change one class, which is called the controller class, and there are two methods in this class. They're called packet was sent and ACK received that you should change. That's the idea. You can also change other parts of the code, so you can change the sender and the receiver if you so wish, but you don't need to. So the only thing that you really need is to look at the packet was sent and ACK receive methods. The first is code that specifies code that is executed whenever a packet is transmitted. So you can update some variables and stuff like that. And the second part specifies code that is executed when an ACK acknowledgement is received. So these are the two most important big bits typically in a congestion control algorithm, and these are the ones that you should fill basically. So in terms of metrics, we will measure the long-term throughput of the protocol over the entire trace and the delay. The delay is a very specific type of delay, end-to-end delay, so it's also called signaling delay, and we go for the 95th percentile because we want to guarantee that delay is always or most of the times below a certain level, that it's not very high. And end-to-end delay is more is good from the application point of view. Like for if you have a video application, the video application cares more about end-to-end delay than, for example, per packet delay. And then the score is calculated using this formula. So you have three exercises, two warm-up ones, where the first is you just have to vary the window size, just there's a fixed number, and then make a graph and try to reason about it. And the second is to implement a simple additive increase, multiplicative decrease scheme similar to TCP's congestion avoidance phase. If you click on the link, you have a Wikipedia. Well, you don't have the link here, by the way, but you will have the slides in the course webpage. And so just a simple scheme as we talked in the lectures. And then it's the contest itself. So you can try different approaches, could be loss-based, delay-based, could be prediction-based, whatever, let your imagination roll, and you should work to maximize your score on the final evaluation. Be wary about overtraining, don't look much at, try to build a scheme that makes sense, but that you don't overtrain to the trace that you have, because you have only one single trace, so you may look at the trace and try to improve just by looking, okay, so this trace is like this, so I should do it like that. Effectively, I will give you like a second trace later, so like in a week or so that you can then check if your algorithm is working well even on a different trace, because then in the end we will evaluate this using several traces, like 3 to 5 different traces. So in terms of what results are to be expected, ideally you would get something like this, something that has high throughput, as you can see on your left. You can see that the blue line is the protocol, and it's quite often taking advantage of the full capacity of the network, so it's very high throughput, very good. On the right, you see that it has very low delay, 95th percentile on 136 milliseconds. This is very good. This is very good for a video conversation or even for a Skype conversation. This would be the best. The worst would be something like this. So, zero throughput, or very, very low throughput, and a huge delay, 131 seconds on your right. So this is really just an example that's not very realistic. It's just sending one packet like in the beginning and one packet in the end. So basically sending nothing. But anyway, just an example of this would be the worst possible case. Then there are several in the middle, like you can have high throughput and high delay. So high throughput on the left, high delay on the right with 1 second delay. This is typical like on conventional TCP because TCP just tries to fill up all buffers, and so delays tend to accumulate. So this is a problem when you have large buffers especially. Or you could also have low throughput and low delay. Of course, if you send just, if the throughput is low, if your window size is small, then you're not filling up the buffers, and then the delay is low, which is, can be okay for certain applications like, I don't know, a Skype call probably doesn't have that much capacity, that much throughput needed, but, you're really not using the full capacity of the network, so for video this could be problematic. Finally, I show an example of results from other students that have made the contest. This is like 3,000 samples from 3,000 student protocols, and it's interesting that we see that that seems to exist an achievability region. You see the omniscient, which is the solution that would know exactly what's happening in the future, that has the lowest delay, which is to your right, and the highest throughput, which is up. And you see the Sprout algorithm that we talked in the lectures, which also achieves a very interesting result. But the students' results are also, they tend to cluster around, close to something that's quite interesting, but they seem to make this achievability region, which is interesting. This pink or red curve it kind of shows that it's hard to do better than this. One caution, as I mentioned before, overtraining effect. You see in here results with the training trace on your left and with the testing trace on your right, and you can see that like the results from the students in the training trace, they are better and more clustered, like in the better place, than on your right, where you see that they are more spread, so they are not that good. So this is probably something like overtraining effect. So in summary, almost all students in the past have submitted protocols that performed competitively. For some, there was some degree of overtraining. It's also interesting to see that achievability region, which, it's an interesting outcome too when you have like lots and lots of student protocols being submitted. And in the end, interestingly, there were 2 student protocols that performed slightly better than Sprout, which is the state of the art. So effectively, a design contest as this one can improve the state of the art, right? Okay, in the next video, I will show you a demo.